I'm just presenting a series of 4 YouTube videos based on some analysis work I did for CanMet. It's generally called mineral processing analysis, but basically I'm taking flotation data, I'm analyzing it, and from that constructing a simulation. There's quite a number of unique capabilities that I've developed, which is why it's a series of YouTube videos. So I've developed a simulation system. This simulation system is Excel based. It's a flowchart system in Excel. And there are courses to explain the methodology. Now, of course, the more you go into depth, the longer you take in a course, the more you can understand. So I've got some videos which are fairly holistic. So you can look at it and go, oh, right, I understand what you're doing, but I wouldn't be able to do it myself. The simulation I've constructed is fairly schematic. It's not yet at a point I would implement it in a process plant because there's not enough information. But it is still useful for explaining the concepts. So there's 3 main methods as part of this overall analysis approach. There's principal component analysis, there's model fitting, and there's simulation. All these 3 components I've developed myself. And so each of those are their own separate YouTube videos. All these YouTube videos are overviews only, and detailed Udemy courses will be prepared if there is sufficient interest. So if you like this video or you like the other videos, please indicate that yes, you would be interested in doing a Udemy course. Really, my cutoff is about 20 people. If I get 20, that certainly gives me justification to provide a Udemy course. So this video itself is a holistic overview, and then it's subdivided. The next 3 ones are overviews themselves of principal component analysis, model fitting, and simulation. And then if you want to do the in-depth courses, they're available in the yellow. So what is principal component analysis? For a start, I doubt that there's any mineral processing engineering course in the world that would include principal component analysis. This isn't because it's not relevant to mineral processing. It's more to do with the fact that mineral processors aren't aware that it's relevant to mineral processing. Now, the simulation will be in flotation. There's 2 schools of thought about flotation, and I'm a bit embarrassed to talk about the first, which is that flotation causes minerals to float. The second is that flotation causes particles to float. Now, clearly, every mineral processor knows that it's particles that float. Yet, when it comes to the modelling, they model the minerals floating. They use what's called a floatability component approach. So this first approach is convenient, whereas method 2 is realistic. Principal component analysis is used to take data and determine common particle types. Now, my background, I did a lot of work in mineralogical analysis, and I'm not saying don't use mineralogical analysis. The trouble is that there's no, I know that's a generalization, but there's no systems out there which are user friendly. And so we're forced to rely on assay data and plant data rather than mineralogical data. Now, it is well known that the realistic approach is method 2. The problem is people don't know how to do it, particularly when you want to try and link in comminution with flotation. So here's a multi-mineral particle, which is the logo I use for my company. So there will be a variety of minerals and complex ores. Purple here might be hydrophobic, but the red might be hydrophobic as well. So it doesn't make sense to say that the flotation is dictated only by the amount of the purple. But we're not going to get into multi-mineral particles too much here. So principal component analysis allows us to determine common particle types, and those particle types are simulated. But what we also want to know is, for these particle types, what is the kinetic rate? How well do they float? Now, I tried doing this with Excel, and Excel now gets limited. It was awful to use. So I had to create my own solver algorithm, which is available in the in-depth course. And then the third step is simulation. Once we get the kinetic rates, we can create a flowchart of the desired process and simulate. So here's the flowchart I'm simulating. There's 3 flotation cells. I'm getting the kinetic rates from the data. So the data as supplied was this. So we have a cleaner 1, 2, 3 and a rougher con. I'm not using the rougher con data because after the rougher con there's comminution, and the client decided to keep this particular video focused on flotation. Later videos will talk about linking in with comminution. We won't go through the data here in depth, but it's fairly typical flotation data. We do that, we get the kinetic rates, we create the flowchart, and we simulate. And we're not going to go over this in detail, but we can simulate this and get our final con given the feed. So that's the end of the overview. Thanks for listening. And if you're interested, we'll be looking at those 3 facets in more depth: principal component analysis, model fitting, and simulation.